Mhm.
Hello, everyone. Thank you for joining us today for this webinar titled Advanced Automation for Winding of CNG and Hydrogen Tanks. It is brought to you by CompositedWorld and presented by Microsom. My name is Ginger Gardner, and I am Senior Editor at CompositedWorld. Composite pressure vessels, CPVs, for high-pressure storage and transport of compressed natural gas, CNG, and hydrogen, are one of the fastest-growing markets for advanced composites. The growing demand, especially for high-volume production of tanks for hydrogen, is forcing Tier 1 and equipment suppliers to think beyond traditional filament winding and demand equipment with higher quality control, lower cycle times, reduced downtime, improved material handling, and increased integration with all the steps in the production process. Microsom is at the forefront of automating the filament winding process and is currently delivering several automated line projects for CPVs, serving the global transportation and storage market. A fully integrated solution may include several single or multi-spindle winders for wet and toe preg winding, along with units to support the operation prior to and after winding. Tier 1 suppliers and OEMs can achieve scalable, world-class operations for high-volume CPV production. In this webinar, attendees will learn about the proven solutions for developing and producing high-pressure storage tanks, including considerations for automating and scaling such production. Our presenters today are Vele Samak, Chief Revenue Officer, and Dimitar Bogdanoski, Sales Manager at Microsom. Vele served in various international roles before joining Microsom, including marketing, business intelligence, and server software at Microsoft, developing quantitative investment strategies for pension funds at Citigroup, and creating foreign investment jobs in Macedonia. Vele holds degrees from the Wharton School and the University of Chicago. He is a U.S. citizen and a native of Macedonia. Dimitar has 18 years of experience in delivering successful automated filament winding systems to companies across the globe, from early turnkey solutions for composite LPG tanks to some of the most advanced and largest lines for CNG and compressed hydrogen gas tanks. Dimitar has developed an extensive know-how in CPV production and how to meet customer needs worldwide. Dimitar has a bachelor's degree in marketing management from Fontys University in the Netherlands. Before we begin, I'd like to remind you to please submit your questions by typing them into the Q&A pane on your control panel at the right of your screen. We will answer these during our Q&A session at the end of this presentation. And now I'm going to hand it over to Vele.
Thank you, Ginger, for this lovely introduction, and welcome everyone to attending this webinar from Microsom. We're glad to have you all. I think it's good morning, good day, or maybe good afternoon in some locations. So we're very excited to be presenting this webinar to you. Our agenda today, the topics that we'll try to cover, with a little bit of Q&A time, include just a quick introduction on Microsom, what we do in terms of filament winding, scaling, hydrogen and natural gas composite pressure vessel winding, and a case study for such production. So right off the bat, some of you are probably familiar with Microsom, some of you are perhaps learning the first time, and some of you are perhaps learning the first time about filament winding capabilities. So I will run a little bit through what is Microsom and what we do. Our vision is to have automated manufacturing with advanced materials, and our mission is to be a leader in such solutions for advanced composites. So a little bit about the company. We're based here in Prilep, Macedonia. We were founded about 32 years ago, and we have extensive experience in composites production and machine building. All our machines are engineered to order, and we have specialty expertise in composites, in motion control, and process automation, and we have our own software development team. Microsom is now almost 200 people. It's an engineering-driven company. Everything is built, designed, tested, and shipped out of facilities here in Prilep, Macedonia. So over the last 30 years, we have delivered more than 300 different production lines across the globe in over 40 different countries. And pretty much everywhere where there is a growing market in composites manufacturing, we have a Microsom machine or production line installed. So one thing that's unique about us is that we are in some ways a one-stop shop. We have a number of different production categories, from pre-preg machines, slitting, rewinding machines, fiber and tape placement, filament winding, and automated solutions. All of this backed and supported with our own software. So just a few brief slides on just some of the pictures of equipment we've delivered outside of filament winding. You see here some impregnation lines for hot melt resin systems, solvent, thermoplastic, and toe preg equipment. You see here some of our growing, this is a growing segment for Microsom, the slitting and conversion of prepregs. And of course, fiber and tape placement machine with a range of configuration, robotic or gantry style configurations. You can see a number of different machines for tape laying capability that we have delivered, and also for fiber placement capability that we have across the globe. So all of this is tied with our own software that comes specifically with each machine. Microplace for AFP, Winding Expert, which is heavily used in our filament winding equipment, and quality control system and micro automate. So that's a little bit about Microsom's other product categories. I'll touch a little bit about Microsom's filament winding history, which is the longest product line that we have before I jump into sort of the meat of the presentation. We are known as one of the technology-focused companies in filament winding, globally present, and with a few patented solutions and industry firsts. So a number of these areas have put us as a continually innovative supplier for filament winding equipment. Anything from multi-spindle machines for either serial production or product development, large format floor pad configurations in what you see here, multiple axes up to 6 axes or more if you had robotic configurations, and specialized filament winding units for R&D purposes, or hybrid, which integrate winding and fiber and tape placement operation. So out of these machines, which can be used for product development and certification, we have extended our market leadership and know-how in automating lines for high volume of production of composite pressure vessels, anything from LPG, CNG to hydrogen nowadays. So we'll spend a little more time in that. Before we jump, I will do a quick video here just to underscore some of the variety of capabilities of the winding equipment from Microsom. This would be examples of these portal-based 2-spindle, 3-spindle machines, which can be used for R&D, for product certification, for example, for CNG or hydrogen tanks, wet winding or dry winding capabilities, tied with our Winding Expert software that you see here, a range of different creel solutions, resin bath solutions, different levels of automation or very little automation, depending on sort of what's necessary. But suffice to say, if you're in the starting out in developing pressure vessels, then this would be one of the types of machines that you can see. Here you see a toe preg winding that's currently used in automotive production with a tier 1 automotive customer. So you will see a number of different units, pressure vessels made in multiple spindle solutions that employ both carbon fiber and glass fiber materials. So for some of the customers, some of the people in the audience, this could be the first time that you see here. Here's some of our latest machines, for example, where we do product development using toe preg winding for compressed hydrogen gas. You see the level of precision and automation in a compact type of manufacturing, which could be used for the initial serial production or product development and certification. So usually some of these units help you do the initial development. You do some testing, small batch ovens for curing capability, all the way to large floor bed type of machines, again, either toe preg or wet winding, that demonstrate just this range of capabilities that Microsom has today on the market. So the context for this video is just to give you a bit of range of what's capable, the level of experience that we have put out there. Before we jump in terms of how to take this and scale it to large volume serial production. So it's an example of complex winding, 6-axis motions, all programmed and controlled by the Microsom software. So you see small tanks on these large machines because that's what we have in our factories. And then right here is a robotic capability attached to a large floor bed machine, again for pressure vessel winding for very specialized applications. So with this in mind, you have a good understanding of what Microsom has been capable in delivering to customers these past three decades now. So the question then on everyone's mind is, how do we move this forward into serial production with consistent quality and large scale of automation? So just a range of products and Microsom experience in anything from LPG to CNG and to hydrogen tanks today. So to understand the market, the high volume production of composite pressure vessels, I'll put together this slide, which should give you a little bit of the different scales, product dimensions, and production issues. So what you see is different volumes of LPG tanks, CNG tanks, and hydrogen tanks. So LPG tanks are probably the highest volume pressure vessel product out there on the market today. They typically range in 500s of thousands to several million per year. The sizes do not vary a lot. All have very similar diameters, and anything from 18 to 35 liters or so. Low pressure, mainly glass fiber, and short cycle times, less than 5 minutes, and you can get down to even lower as you scale that operation. So not a lot of product variability, but huge volumes and short cycle times. You move from LPG to CNG. Now the issue is two types of material. Typically it's carbon fiber, some carbon fiber layers, some glass fiber layers, much higher pressure now, almost 10 times as much pressure, and also much bigger variation in products. So anything from 40 liters up to 500 liters in some configuration to the 2,000 liter products that are out there in the market. So in this case, we're looking at thousands to tens of thousands of such products with varied cycle times ranging from half an hour to a couple hours or more. And finally, so this is an established market with the different applications on the CNG tanks, but the hydrogen tanks is one that's in a lot of demand, a lot of growth potential, and we're all waiting for that hockey stick to kick in. But the crucial point here is that it's largely carbon fiber driven material on the composite tanks, much more material per tank. So sometimes you have a lot of material per tank going in there. And cycle times are, of course, going to grow as a function of that requirement. The scale today is in the hundreds to a few thousands. The potential is that we see from several thousands and more. So, it's a question of how do you scale this? Where do you grow? Where the capacities are? Now, the reason for bringing all this up is because this all creates different challenges. If you're producing LPG today, you need a fast multi-spindle machine or maybe a twin machine. It's a single glass fiber resin combo, short cycle time. So you want this machine to run as fast as possible, and you want the liners just to come in there and occasionally replace the glass fiber and the resin into the machine. So here the issue is how do you arrange the curing and the automation for the curing? So now you can have one or two winders with 4 or 5 spindles, but very large continuous curing ovens. Now, as you move down to the CNG setup, now all of a sudden you have to deal with two different types of materials. Now, do you have of course multi-spindle winders, but do you use dedicated winders for each material? Do you use dual carriage? What is the range of products that you will be running across the line? This longer cycle time now all of a sudden dictates what kind of buffering you will have before and after this the winding. And suddenly the material handling, which looked simple for the LPGs with one robot and a simple gripper, now all of a sudden you have to consider robot, weights, all sorts of other parameters into the picture, and even going up to the gantry type of operations. Hydrogen production is similar to the CNG type of production. But here, the challenge now becomes even more based on the material. Okay, you have way more material per product than what you do in the CNG. So how often do you change? How do you change it? How do you manage that downtime? All of that drives the cost process. So we will talk a little bit about this. And with that, I want to keep in mind some of the considerations as you take a particular product, whether it's a CNG or hydrogen tank, and what it means for you to get to a good automated filament binding line. Now, the key point here is that we all want highest productivity, reduced downtimes, and the flexibility in the line that we get high ROI. So all these issues that you see here, you want a good quality machine. You want to understand the flexibility in the product dimension across the winders and so forth. All of these are consideration you have to know beforehand or have some visibility in order to plan out how you are going to produce this automated line for filament binding of these types of tanks. In the end of the day, how you resupply material, what level of human interaction is in there, and what kind of startup support and integration with the remaining portions of your factory production are going to be critical in making sure that's a successful setup. So let's look at something that makes that's already functioning and how that works today and what lessons we can drive from this. So one of the currently largest lines in operation, fully automated lines, produces about over 60,000 different sizes of CNG tanks. So it uses over 24 different servo motor controlled axes, 4 types of different products. And you see a little bit on the schematic what that actually looks like. You'll see a video in the end of its actual run in production. So when you want to go big and go something like of this type of scale, the winder is going to be only one of the many components that you have to account for as you ramp up this line and plan your investment. This is a bit of a schematic view of what this means. So, you have a different, once the liners are produced, assembled, there's a boss part in there, there's shafts in there. Anything that goes in from the liner as it moves through the winding stations and then down to the curing ovens and out of these curing ovens is what we would consider an automated line for filament binding. So here we'll cover the 4 key components that fall into this place, and we'll look at a scenario at the end of what that means. So we'll look at the winding cell, the liner and tank handling, what happens with the curing, and then the synchronization. Okay, so when you're looking at the most critical component is, of course, the filament winding equipment. How big of a machine or machines you need in this case, and how do you balance that initial capex? Of course, everybody wants a lower capex today, and with the uncertainty of, say, product demand or flexibility down the road. So one of the things that drive these decisions are usually around what products will have your highest volume and what range of products you eventually want to produce on this setup. So ultimately, multi-spindle machines are the ones designed to accommodate these types of volumes. Okay, and if you're looking at typical sizes where the length goes up to 4 meters or so, typical portal type of configuration. and what ratio of the material. Now, dual carriage is an interesting solution because it allows the same machine to wind both carbon fiber and glass fiber. So if your capacity requirement is not big initially, this is a great first step. But ultimately, it's not a great solution if you're growing or if you already know that the capacity is going to be much bigger. If half the system is effectively idle and doesn't give you a lot of flexibility in case unforeseen things happen. So one of the obvious situations, if you have a very low volume of glass fiber that's included in this type of CNG product, then mainly having dedicated carbon fiber versus glass fiber winders can be a more economical and a more scalable solution. This allows you easier and phased ramp up of production, proper training, and then process correction. So that's just an overall view of what to think and how to think about the filament winding configuration. So as we look into the winders, you can designate an RFQ and put all sorts of requirements in there. But what does the automating filament winding cell mean? It means that loading and unloading of these machines has to be automatic, right? So someone has to load the machines and unload the machines. So if it's not an operator, then it has to be some kind of a robotized or gantry type of system. So the machines have to be able to handle this. The start and stop of the winding needs to be automatic. And then as you have diverse tank sizes or product sizes, then winding programs need to be automatically adjusted, not at the station itself, but well beforehand. So the liner and tank handling units have to be able to manage the material drops into the winding station. So this also means that you have to consider some buffering. Buffering gives you a little bit of freedom in the operation in case something happens. So this is a low-cost way of handling automation and building in some redundancy to avoid the fragility of a tightly coupled system. So some of the key components in an automated filament winding machine include a cut and restart system. We've had a patented solutions for a long time that's proven in the market, does a good job. And unlike what's typically available, this is a very flexible solution that adjusts itself to different diameters and liners. It has a cleaning capability, rolls off on the tanks very easily, as you will see later on. So this allows seamless operation, pretty much no human interaction in this process. Okay, so adjustments of the tanks for different product sizes, liner pressurization along with programmable checks, and then winding is a question of properly laying down the fibers, having the right resin and fiber content. So knowing how much tension is built into the winding process, how much fibers are actually in there, and how much material you've consumed is a way to optimize this process, especially as you require traceability down to each individual tank. So these are the types of features that ensure you're not wasting any material and everything goes well in such winding operation. Of course, winding programs, loading and monitoring is one of those things that has to come with this type of automation. So wet winding, as it's really the bulk of the winding operation today, will require dealing with resin baths, not always a fun experience for anybody who's been on the production floor. So you need a seamless type of system, usually having one active resin bath and one second as a replacement. These can be very low cost solutions to ensuring that pot life is properly handled as the machines are running. There's a proper resin mixing system integration in there, and the dosing is correctly measured. So this system allows for pretty much no downtime or minimum interruption and continual monitoring of the process of each wound tank. Now, as you move from CNG to hydrogen tanks, spool replacement now becomes an issue. All of a sudden, you're using, instead of maybe 2-3 products with a single spool, now you need 2 or 3 spool replacements to produce one hydrogen tank. That means a lot of downtime. As everyone knows, opening and closing these creels, putting new material, splicing, continuing, that's significant downtime, whether it's a dry winding or wet winding. So this is one of those, again, economic approaches to reducing downtime and ensuring that the winding cell runs as much as possible. This is some of the items that go into some of the state-of-the-art creels. Now, when it comes to toe preg or dry winding, now this requires not only high speeds. I mean, the high speeds are available in the motors themselves, but also very careful management of the tension system and ensuring that the spool comes out properly and ends up where it needs to be without breakage, without slippage, without fuzziness, and so forth. So we have some extensive experience in this area to produce high quality, fast toe preg winding in this area. The splicing now, especially if you're moving to hydrogen, becomes a critical item. This is an area that we have some capabilities. But this will be your moment or operation of downtime where you want to ensure quality splicing to continue the winding process. Okay, so the 2 points where the liners and the tanks go into the winding cell and out are ones that help the winding operation be uninterrupted with maximum utilization. So liner stations or buffer stations can be the same. It can be very simple units of just hanging up the liners for a quick check, quick storage in case something happens, any issue that happens with the winding operation. You need some way to remove the tanks if they're finished, or something happens following the line, or there's a breakage in the curing or other things. So these are ways to manage this. But not only that, they add to the complexity of product categories. You have different product categories, sizes, so you need some kind of stations with adjustable sizes, and dimensional and weight measurements that get recorded through the system. So what is the weight of the liner that goes in? What is the liner tolerances that come out of your blow molding or roto molding or other stations you have prior to that? Can you batch and organize these together so that the winding programs on a multi-spindle machine are in sync? So all of these issues can be solved if the right liner and buffering station. Also, the buffering station handles if you have dedicated winders for carbon fiber and for glass fiber winding. So this is one critical way to introduce some safety in the operation and further automation. And finally, you've seen a lot of videos and you'll see some more. A lot of the liner and tank handling can be done mainly with robots, linear axis and robots. The key issue is what are they holding and what are they picking up, right? So having the right gripper with proper information, you can do liner and weight measurements without downtime in this case. So if you integrate it right onto the gripper stations, you can ensure that the information is properly handled each step of the way. The weight of the liner before it goes into the winding machine and after it comes out in the winding machine, coupled with the amount of fiber spent and resin used during that process. So the last comes in this process the curing cycle, and here you have a range of continuous or batch configurations. They can be designed to match different curing cycles, variety of temperature zones, large volumes. Continuous curing ovens for LPG tanks range in the hundreds. Continuous curing ovens that we've made and range in the 50 positions or so if it's CNG tanks or multiple batch ovens, which can be managed with different curing cycles. At the end of the day, the first 4 points in the slide are critical. What is your available and future production layout? What is the curing cycle and how much does it vary from product to product? And what happens with the loading and unloading of these ovens? You can add or think of other units to attach to the filament winding, any kind of transport section, visual checks, measurements system, leakage stations, and so forth. So we try not to reinvent the wheel. within some of this scope, Microsom has designed some units like what you see here, but we have excellent cooperation record with many third-party suppliers before the liner station, blow molding, rotomolding, other companies, and other testing solutions. So we have a very good track record in these turnkey solutions. So finally, putting this all together is our quality control system, and this is a way that you track everything that happens with each individual liner as it comes out of the blow molding operation and leaves the oven and enters the customer area. So there's all sorts of ways to record data from liner pressure, stops, fiber tension, usage of material, weight, and so forth. So it can be linked and tied to your manufacturing system and so forth. But having multiple units in an automated filament winding line also means that you need synchronized automation and handoff between each units of the product, and understanding how that affects the quality of your composite pressure vessels. So our two products here have successfully been proven in the market to work very well and ensure quality at the end of the day. So this is just a few of these screenshots, just how it looks from an operator perspective. That means you're putting the human operation at an optimal level. You cannot replace or completely eliminate. So this is a way to ensure that they have the right view in this process. So as you've seen this overview of what an automated line looks like, we will run through a quick case study and what it means for your production. I'll hand this over to Dimitar to just let you know how this.
Okay, thank you, Vele. So, yeah, for many of the viewers of this webinar, I believe would be interesting to see a sample of one cost calculation about a typical product, no matter if it's LPG, CNG, or hydrogen. With almost every customer, we come to the interaction and discussion about how much the product will cost before, of course, entering into investment. So here we would like to show you one case study for production of CNG tank at 200 bars working pressure. The volume of this cylinder is 90 liter, and it is intended for the use in the automotive industry. So this cylinder can be built either from carbon fiber, glass fiber, or hybrid one. And of course, there is a cost comparison between using all these three combinations. Operating pressure of this cylinder is 200 bar, and the burst pressure is over 700 bars. This cost calculation we did recently for one of our customers before he made the decision to enter into the investment. And his target for the annual production capacity was between 40 and 45,000. So for this specific case, we came to calculation of 42,000 pieces per year. And of course, the design is very important. So we selected for this case to go with the hybrid design, consisted of carbon fiber and glass fiber, and percentage of each of these fibers is around 50%. So we came to the estimated cost for production of one cylinder of almost 290 euros, which gives you an average cost of the CNG cylinder per liter volume of 3.20 liter. Here we are showing you a rough calculation of the capacity requirement to underscore the optimization of the line for a single product. The target, as I mentioned, the target capacity was between 40 and 45,000 tanks per year. And it's consisted of multiple equipment units, which is automated filament winding machine. In order to realize this output, we need one high-speed and high-precision winding machine with 4 spindles. Then we have 2 winding carriages, one for carbon fiber and one for glass fiber. We have also automatic cut and restart system, and for the design, we choose 8 fibers per spindle, which means 32 spools of the fiber krill per carriage. one with electronic control of the tension of the fibers, and another one with simple tension control for glass fibers. And we have a manual or automated spool splicing station to minimize the winding downtime. Besides the winding machine, which is main driving point regarding the production time, we have a liner tank handling, which is done by the robot system that can unload tanks and load empty liners. Then we have a liner storage and batching station. And as Vele mentioned before, we have also involved the buffer station, which is very important in the whole production cycle. This is used for holding the tanks before entering the curing over or in any other station. And we have a conveyor curing oven, and we also have automatic oven loading and unloading. Winding cycle, in order to produce this one size of 90 liter CNG tank, is 34 minutes. And here you can see how this is spread out through different functions. Just to mention, the diameter was around 360 millimeters and the length was 1.1 meter. 1.1 meter. So for loading and unloading, we need around 1 minute. For automatic fiber cut and restart, also 1 minute, both for carbon and glass fiber. Then, since I mentioned it's 50% carbon fiber and 50% glass fiber, we need around 16 minutes per each winding fiber. And this gives us a total cycle time of 34 minutes. We took efficiency of the overall equipment of 85%, and with four spindle operation, we come to overall equipment efficiency of 6 cylinders per hour, and in total, in 300 days, we can reach around 44,000 pieces per year, which meets the required output of 42,000 cylinders per year. In order to realize all of this, we need only one filament winding. We can reach with one filament winding machine. Here you can see the total cost overview for the CNG at 200 bars pressure. Out of this, 230 euro, which means almost 80% goes to the for the raw material. And the other costs which are taken into consideration are 5 years depreciation of the equipment, 10 years depreciation of the workshop, and we have also included the labor cost and power consumption. Out of this 230 euro for the raw material costs, almost 60% goes to the carbon fiber winding. Then around 17.5% goes for the boss part, and 12% for the resin. Please note that these calculations are done with the average price references from February this year, and due to some price increases recently, some of these costs might be even higher. Regarding the cost of energy, we took total installed power for all equipment units, which means also blow molding equipment, testing equipment, and liner preparation. And with the current prices of the energy, this reaches to the 3.5 euro per cylinder. One note here again, so this is done for a customer in Asia. Very important are also to consider the cost for the labor. So number of employees that we need to realize this production output is 30 for 3 shifts, and part of these are on the blow molding equipment, part of the liner preparation, and the remaining on the filament winding and testing equipment. Cost of amortization of the production line for this specific case is around 10 million euro. And in this 10 million euro investment are taken into account investment in the development and certification of the CNG tank, then for the blow molding equipment, liner preparation, and filament winding and testing equipment. In order to become now more clear for you what we have done in the past years in these automated production lines. We are going to show you some videos where you can see different automated production lines for LPG, CNG, and hydrogen tanks. So typical investment scenarios we have here are shown for LPG, CNG, and hydrogen. So for LPG, ranges that we produce in the winding machine are typically from 12 to 35 liter. The annual output is 350,000 pieces plus, and the production line includes automated winding machine, handling, resin mixing, and conveyor oven. Average investment is around 2 to 2.2 million euro. On the other side, for the CNG, typical investments that we are receiving recently are between 120 and 350 liters. Annual output up to 60,000 pieces per year, and this is all done in the completely automated way, which means automated winding machine, automatic handling, and conveyor curing oven. Here the investments can range between 6 and 7 million euro plus, depending on the level of automation. And the last scenario is for hydrogen tanks. Here inquiries that we are getting are between 250 and 450 liter, with annual output of 30,000 pieces per year. Again, fully automated line, and typical investment is between 10 and 12 million plus. Maybe we go to the next slide. I think we have still a few remaining minutes for the presentation, and here we'd like to show you some automated lines that we've done. So here is typically one LPG production line for output of 350,000 pieces per year that you can reach with one filament winding machine. This is consisted of liner loading station, robot handling, filament winding machine with automated functions, fiber quill for glass fiber, resin bed, and automatic tape tensioning and conveyor curing station. This production line can produce tanks from 5 liters up to 48 liters of volume, and switching from one size to another during the production process is done automatically, which means that here you can see the example of that, which means that filament winding machine can adjust for the new cylinder size by automatic movement of the tailstock to accommodate this new cylinder length. On the next video, you can see one of the most advanced automated filament winding production lines for Type 4 CNG tanks for one of the largest OEMs in the automotive industry. It is also consisted of multiple equipment units, starting from loading station, where by barcode scanning of the liner we are entering the serial number into the control system, and by this serial number we are tracking the complete production process of each cylinder. After automatic loading of the liners onto the filament winding machine, with automatic cut and restart unit, we are applying fibers on the plastic liner. Then winding process starts according to the filament winding program. And winding machine, as you could see, is consisted of two winding carriages, one for carbon fiber winding with dedicated fiber krill and resin bed, and one for glass fiber winding, also with dedicated krill and resin bed. During the complete production process, all process parameters like fiber tension, resin temperature, winding time are recorded and stored in the quality control system. Switching from carbon fiber winding to the glass fiber winding is performed automatically. And after finishing of complete winding program, liners are transferred to the buffer station where also is done a visual inspection or putting a label. As mentioned earlier, changing of production process from one size to another with the different liner diameter and length is done automatically. And in order to do so, for every function of adjustment, there is integrated motor. Next phase of the production process is curing oven. And oven is designed based on the resin system used and required curing cycle. In the oven, we have a constant process of continuous rotation and translation, so that resin when the resin drops down. And in the oven, we have also continuously recording of the curing temperature. Final step of this production line after curing oven is a drop-off station of finished cylinders. And after this station, the cylinders are taken over for the next phase of the production process. On the next video, there is another example of automated hydrogen production line for cylinders with volume up to 300 liters. Winding machine is consisted of 4 spindles, and there is robot handling 2x2 cylinders. Here on the winding machine, we have a constant air filling and monitoring function, which is very important for good quality of winding process. And resin adjustment at the resin bed is individual for each spindle and is performed by motor. Resin filling is also done automatically by resin mixing and refilling station. Again, after finishing of the winding process, here you will see the robot performs unloading function, and here this process is less than a minute. These are a bit heavier tanks. And the final video that we decided to show you today is one of the largest production lines for CNG tanks that is installed currently and is operation at our customer DPO Plastic. And this is dedicated for production of cylinders from 40 liters up to 350 liters. It is also a fully automated production line, which is consisted of multiple filament winding machines, automatic robot handling units, and conveyor curing oven. So based on the cylinder design, which is consisted of glass fiber and carbon fiber, we have decided to offer separate winding machines for carbon fiber and separate winding machines for glass fiber. This makes production process for the customer more effective. And finally, after glass fiber winding process, cylinders are transferred to the next phase of the production process, which is visual inspection and labeling. And finally, I would like to point out that operation of all equipment units is done from the central control cabinet, where we have installed our proprietary Ticon system that is used for controlling of operation of each unit. Here we have a quality control system that collects all process parameters, and moreover, this can be connected with third-party supplier equipment like blow molding and testing equipment and can collect the data from them as well. So, why stay with Microsom? Obviously, we are relationship focused on customer success. We do joint development and research. We also provide 24/7 support system, including remote maintenance and free software upgrades. We use off-the-shelf components from and materials from reputable suppliers, and we have a long history, profitable international presence with offices and representatives in key markets around the world. So, thank you.
Thanks, everyone.
Thanks, everyone.
That was a good wrap up, and just in time. I see a lot of interesting questions, so I bring it back to the host to cover, pick which ones they want us to start with. So,
Okay.
Go ahead, Ginger.
Just to let everyone know, this webinar is being recorded and will be available to everybody after the webinar finishes. We have a ton of questions on thermoplastics. What is your view of them? Are you doing research and development? Can you use thermoplastic prepreg? Wide range.
Thanks, Ginger. Let me answer this very quickly. I saw that there's quite a few of those. It seems very promising. We have done a few trials from customers who have provided us thermoplastic prepregs and specialized liners. This is still a technology, I would say, many years out. We will have volume Topreg tanks production economically before I think we have some thermoplastic, unless there's a major breakthrough. It's an extremely expensive material. at this point, and matching the heating properties of the thermoplastic material to the liner is probably one of the most critical aspects. In these trials, we've done thermoplastics with our fiber placement machines and laser heated source onto metal liners, but also we've done this in a very controlled experience to plastic liners as well. It's promising, but it is far away from anything that will result in an actual product. I would say in the near future. I'm not discounting this at all. We do a lot of thermoplastics work, but as far as this is concerned, it's still very, very early.
So one of the questions was about the liners. What is the typical liner material? And it looks like you don't make the liner modules. You supply those in from key suppliers that you work with, yeah?
Yeah, well, typical materials are HDP and polyamide. And you're right, Ginger. We are not an experts in plastics. These are produced by either by blow molding or in some cases with roto molding. And in order to realize turnkey solutions, we are also in touch with consultants which are pretty good in plastics design and selection of the proper plastic material for specific product, no matter if it's LPG, CNG, or hydrogen tank.
Okay, and can you make it very clear what the difference is between toe preg, pre-preg, thermoplastic, and wet winding? Because toe preg and pre-preg, I think there's a little bit of confusion.
Yeah, let me cover this. Okay, so what you've seen a lot of times is winding equipment, which most of the pictures you've seen is with wet winding, which is the bulk of what the winding is done today. Toe preg is an alternative way. So it's a pre-impregnated fiber with a certain amount of resin content. That way you don't have the resin bath during the winding process. So the toe preg goes directly from the creel into the liner with a little bit of heat. And this is technically supposed to give you a little more consistent quality and much faster speed. The promise is of faster speeds. We are seeing that the speeds are faster. How fast they get is a question further down the road. There's a number of challenges there. So thermoplastic is completely different. It requires different type of interaction with the liner and between each layer. So I would put thermoplastic liners in a separate category. The wet winding is currently the bulk of the winding. It will get to toe preg winding in the near future as prices come down quite a bit, we hope, and volumes grow before it gets to thermoplastics. So I hope that kind of, without going too deep, and answers it.
So several questions about dry winding, toe preg winding versus wet winding. One question is, what is the standard winding speed for compressed hydrogen tanks, wet versus toe preg? And then what are kind of the performance comparisons?
Performance comparisons would be similar, I would say. Speeds, you can get anywhere between 40 and 100 meters a minute realistic winding capabilities. It depends on many factors. With toe preg, technically you can get very high 5 meters a second, 300 meters a minute. The reality is, because we have experience with customers who are currently supplying toe preg, so a lot of those speeds are confidential. They're not close to what the machines are capable. So going from wet winding speeds of, let's say, less than 100 meters a minute to promised 300 meters a minute with toe preg winding, a lot of challenges need to be solved from the actual spools that are coming in from the suppliers, the tension rolling out, and then maintaining that high tension at high speeds without any breakage or fuzziness and so forth. So there's a lot of know-how with suppliers that we're a little bit hard pressed to, we're not able to share. But it's sort of like saying you have a Ferrari and you can drive 150 miles an hour to work every day. You could drive it a few times or on some roads, but not every day, unless you want to get into unnecessary risks. So we have, due to this experience, some non-standard solutions on how to get these fibers out of the creel and onto the liner at higher speeds and higher tensions to produce the product. But the gap in the material cost today is easily 2x between the wet material and the Topreg material that's available, not enough volumes. So there's still a bit of there's quite a development of interest, but I would say until volumes grow, Topreg is going to remain sort of a potential. I don't know, Dimitar, if you wanted to.
Well, you're right. One very important point is the amount of quantity that there is available of the Topreg on the world market, and we've seen that many want to jump into this industry, but it's not going that fast as expected.
Is there any difference in the machine investment for wet winding versus Topreg winding?
Well, in general, no. I mean, more or less, we use the same winding machine, same fiber creel. The only difference is that in wet winding, we do not have a resin bed. We don't need a resin bed and resin mixing and filling station. And on the other side, when we are using Topreg, we only have to change the transport of the fibers with rollers. And as you can notice in the videos, also delivery eye is a little bit different. So. One important point when using a Topreg is that you don't. The curing time is less.
Okay, that was one question. What is the total cycle time for like a CNG or a CHG tank when you include winding and cure and the transit as well?
Well, we here actually the driving point in the cycle time is the winding time. So. As you see from the sample showcase that given to you, for 90 liter, it's 34 minutes. And based on this time, we are then defining specification or the capacity of all other equipment units. On the other side, the curing oven is related to the selection of the resin system and curing time required. So when we start the calculation, we are taking the winding time, and then all other equipment units are designed in order to match this cycle time.
And all of these resins, typically it's epoxy, yeah? Whether it's Topreg or wet, it's epoxy.
Yes, in most of the cases, yeah.
What happens when during multiple vessels, so we saw the 4 spindle system, when multiple vessels are being wound, what happens when fiber breakage occurs at one of those?
Well, when fiber breakage occurs, of course, you have to stop and connect it. And we have added to almost all equipment, these production lines, we have added splicer, which are in proximity to the places where this can happen. So in order to minimize the downtime.
Do you have any experience with winding tapes instead of fiber toes? So tapes closer to 1 inch in width. And what is the smallest tape weight that you've been able to work with?
Okay, thank you. Thank you for the question. Yeah, we have experience with the thermoplastic tape, not a big experience with the 1 inch white tape. And of course, this is also connected to the size of the cylinder. So as bigger the size of the cylinder, the wider tape we can use. And before selection the width of the tape, we can do simulation in our software and to see if it's possible to realize or not.
Okay, we've had several questions about, can you do linerless or Type 5 tanks? Have you worked with those?
We have some development project, but what I can say, it's we are a couple of years far away to come to the real production of the linerless.
Okay. Can you explain the difference in investment between a CNG and a CHG tank line?
So this question is also related to to one of the previous questions that you asked me. So more or less is the same. The only thing is in the resin bed, resin mixing, and in the curing oven design. So these are some things to mention.
It's going to be different capacity because of the winding cycle time being much bigger, but similar components will be part of that line.
And we've asked if you could present a case study also on CHG vessels. People, the CNG is very interesting, but I think everybody's very interested in hydrogen.
Well, yes, we have such cases, but I think we can, if there is any specific viewer that wants to have this, they can get in touch with us. I mean, for the sake of this short presentation today, we selected the CNG as the most common these days, but we have such a calculations for the hydrogen as well.
Okay, I'm going to do 2 or 3 more questions, then we're going to go. One was about you're using both glass and carbon fiber in a hybrid tank design. Are there not differences in the CTE? How do you deal with that, the thermal expansion?
No, we haven't done, we haven't experienced any differences. So we've done many projects like this, and the final product is compact, and it passes all the tests according to the certification requirements.
What is, go ahead.
No, that's what Dimitar said basically. Through the certification process, these things are tested, force pressure in different hazardous scenarios, and I think this is a proven product.
What is your approach to handling different vessel sizes in the same highly automated line?
Well, as I mentioned in one of the video presentation, in order to do so, we have integrated more than 20 in the typical CNG production filament winding machine. We have integrated more than 24 servo motors in order to move all of these units for the specific size, which means tailstock movement, adjustment of the height of the automatic cut restart device for different sizes. So actually, you need many motors on the winding machine in order to realize so.
All right, one last question. What is the fiber volume fraction that's typically achieved? How high can you go?
What is it?
Can you repeat that?
What is the typical fiber volume fraction, fiber to resin ratio, and then how high can you go? How high is possible?
Well, there are many papers on this. So general rule of thumb is 70 to 30%, and we can go 75 to 25.
Perfect. Thank
and
you.
This is one of the advantages using a toe brake. You can precisely control.
Okay. Well, thank you so much. Everybody has been saying how great the presentation was. I agree. We want to thank Microsom for this webinar. We invite you to reach out to these experts to learn more. And we also want to thank all of our attendees. We really appreciate you being with us. And we hope to see you again at the next Composites World webinar. Have a great day, everybody.
Very good. Thanks, everyone.
Thanks. Thank you, Ginger.
Thank you, Ginger.